Welcome to Large Language Models, a free public course from Bluevision AI. This is session 1, and if you stick with us for all 14 sessions, you'll understand large language models from the inside out. Not just how to use them, but how they actually work, mathematically, from foundations to production systems. Before any of that, though, we need to sit with a question that sounds almost insultingly simple. A question that turns out to be one of the deepest problems in all of computer science. The year is 1950. And in a small office at the University of Manchester, a British mathematician named Alan Turing is about to ask what might be the most provocative question ever put to science. Can machines think? He proposes a way to test it. If a machine can hold a conversation, and the human on the other end genuinely can't tell they're talking to a machine, then, Turing argues, we've got no principled reason to deny its thinking. Simple idea, enormous consequences. He published this in the journal Mind in 1950, in a paper called Computing Machinery and Intelligence. And this paper, this one question, is where everything we're going to study in this course begins. 75 years later, machines write poetry, debug production code, pass the bar exam, translate between 100 languages, and explain quantum physics to a 10-year-old. We've made extraordinary, almost unimaginable progress, and yet, they still sometimes confuse your and your. They fail reasoning puzzles a child would find trivial. They make up citations to papers that don't exist, and they do it with complete confidence. Why? Why is language, the thing every 3-year-old on the planet has essentially mastered, still such an extraordinary challenge for systems that can calculate protein structures and outplay world champions at chess? That's the question this session answers. Every session in this course has what I call a villain, an unsolved problem, a gap between what we want and what we've actually got. And understanding that villain deeply is what makes every solution we build later feel earned rather than arbitrary. Here's the villain for session 1. Language is effortless for a 3-year-old, and it's been a mostly unsolved problem for machines for 70 years. That asymmetry, trivial for a child, yet hard for a supercomputer, is the puzzle we're here to dismantle. And here's something important. This isn't a case of one missing algorithm, where we need a single clever idea and then everything works. What we're actually dealing with is a family of distinct, deep problems, each with its own shape and its own solution. This session is the map. We're going to name every problem, and then, session by session, we're going to build the solutions. To understand why language is hard, it helps to see what makes it different from the kinds of data machine learning already handles well. Let me give you 3 comparisons. Images. Think of an image, a fixed-size grid of pixels. Each pixel is a number, 3 numbers if it's in color. The structure is spatial, regular, mathematically clean. A pixel at row 10, column 20 is always in the same geometric relationship to its neighbors. Convolutional networks exploit this beautifully. Tabular data. Even cleaner. Rows and columns. Each feature has a type, a range, a well-defined meaning. You know exactly what you're working with. A gradient-boosted tree handles this with ease. Audio. A one-dimensional waveform over time. Noisy, yes, but the mathematical structure is clear. You can take a Fourier transform. You know what tools to reach for. Language is completely different. Its length varies from 2 words to 2,000, and you can't know in advance. Its structure is hierarchical. Words combine into phrases, phrases into clauses, clauses into sentences, and the hierarchy itself is ambiguous. Its meaning depends on context that may sit hundreds of words away, and it's packed with assumptions about the world that the speaker and listener share implicitly, assumptions that were never written down anywhere. Language isn't just data, it's thought, compressed. So let me give you the map. We're going to look at 4 hard problems today. By the end of this session, I want each of these to feel real and concrete. Not like abstract categories from a textbook, but like genuine obstacles you've personally run into. The first is ambiguity. The same words mean different things in different contexts, and you'll feel this one within 3 slides. And this isn't the exception in language, it's the rule. Almost every common word is ambiguous. Almost every common sentence structure is ambiguous. The second is context dependency. You can't determine what a word or sentence means by looking at it in isolation. Meaning only emerges in relation to everything around it, and sometimes the words that matter most sit far away in the sentence. The third is scale. Language is combinatorially vast. The number of possible sentences in English is effectively infinite. No dataset you could ever collect will come close to covering them, which means a model must generalize. And generalizing over that kind of space is genuinely hard. And the fourth is world knowledge. Language encodes assumptions about how reality works. To understand what someone is saying, you often need to know things that were never written down. Things about causality, about human behavior, about the physical world. Hold on to these four. Every architecture we study, from RNNs through attention to the transformer family, is, in a deep sense, a response to one or more of these four problems. Let's go deeper on the first problem, ambiguity. The reason this problem is so formidable is that it isn't one thing. It's four different kinds of ambiguity, all operating at the same time. Here's the claim. Natural language is ambiguous at every level of linguistic analysis. Simultaneously. Not sometimes, always. Start with lexical ambiguity. One word, many meanings. Probably the kind you already had in mind. Then comes syntactic ambiguity. The same sentence, more than one grammatically valid parse tree, and the grammar itself won't tell you which. Semantic ambiguity is sneakier. Even once you've settled the structure, the sentence can still mean more than one thing. The words just don't pin it down. And there's pragmatic ambiguity, where the intended meaning differs from the literal meaning. Think of sarcasm, irony, indirect requests. When someone says, "Could you open a window?" they're not asking about your capabilities. They want the window open. Here's the thing that should astonish you. A human reader resolves all four levels simultaneously, unconsciously, typically in under 250 milliseconds. The fact that you've never noticed you were doing this is precisely why it's so hard to engineer. Let's start with the most familiar form, lexical ambiguity. The same word, multiple meanings. I went to the bank. Which bank? A river bank? A financial institution? A blood bank? A bank of fog? All grammatically identical. The only way to know is context. And notice, the context is itself made of words that might also be ambiguous. And this isn't a rare edge case. The Oxford English Dictionary's entry for the word set runs to around 430 senses in its second edition. And when the OED's editors revised the entry for run in 2011, the count came to 645. These are common, everyday words. The ambiguity isn't a quirk of language, it's a structural feature. This is a key insight, and I want you to really absorb it. Words don't have meanings. They have potentials for meaning, which get realized by context. That's not a bug in language. It's how language achieves expressive power with a limited vocabulary. One word does many jobs, but it means a model can't interpret a word without its surroundings. Context isn't optional. Now let's look at syntactic ambiguity. I love this one because it's so structurally clean. I saw the man with the telescope. Reading A. I had a telescope. I used it to see the man. The phrase with the telescope describes how I saw. It modifies the verb phrase. Reading B. The man had the telescope. I saw him holding it. Now with the telescope modifies the noun phrase. It tells you which man. Both readings are equally grammatical. Neither is wrong. This is what linguists and NLP researchers call the prepositional phrase attachment problem. Where does a prepositional phrase attach in the parse tree? It's been a central challenge since the 1950s, and grammar can't resolve it. Only world knowledge can. Who's more likely to have the telescope? Me or some man I spotted? And here's what that actually looks like as structure. So, which reading is right? Let's draw both trees and look at where they differ. Here's reading A. Watch the shape of it. The sentence splits into a noun phrase, I, and a verb phrase. And inside that verb phrase you find saw, the noun phrase, the man, and attached directly to the verb phrase, the prepositional phrase, with the telescope, highlighted in gold. The tree is telling you the telescope belongs to the seeing. Now reading B next to it. Look at the top of both trees. Identical. Sentence, noun phrase, verb phrase. Exactly the same, but follow the blue path. This time, the prepositional phrase attaches inside the noun phrase, under the man. The tree says, the telescope belongs to the man. I just saw him carrying it. Same 8 words. One attachment decision. 2 completely different events in the world. A parser has to consider both structures, and grammar by itself will never tell it which one the speaker meant. Put simply, grammar gives you the options, and only knowledge of the world picks between them. That single fork, repeated across every long sentence you've ever read, is why syntactic ambiguity never really goes away. Now I want to show you what I think is the most elegant example of ambiguity in the entire field. It's called the Winograd schema, named after Terry Winograd, whose 1972 thesis contained the original example sentence. Hector Levesque and colleagues later turned it into a formal test of machine understanding in 2012. This is where it gets really interesting. Read it with me. The trophy didn't fit in a suitcase because it was too big. What does it refer to? The trophy. Obviously. If the trophy was too big, it wouldn't fit in the suitcase. You got that in a fraction of a second, almost without effort. The trophy didn't fit in the suitcase because it was too small. What does it refer to now? The suitcase. The suitcase is too small. That's why the trophy doesn't fit. Notice what just happened. The pronoun it is syntactically identical in both sentences. There's no grammatical rule, no parse tree, no part of speech tag that tells you which noun it refers to. To resolve that pronoun, you need to understand physical causality. You need to know that things fail to fit in a container either because the thing is too large or because the container is too small. That's not grammar. That's knowledge of physics, knowledge of the world, and you brought it to bear in under a second without thinking. This is what makes language understanding genuinely hard. The second hard problem follows naturally from the first. If meaning requires context, the fundamental question becomes, how do we represent context mathematically? And the answer begins with one of the most important observations in the history of linguistics. You shall know a word by the company it keeps. John Rupert Firth, British linguist, 1957. And this one sentence contains the seed of almost everything we're going to build in this course. Think about what it's actually saying. A word doesn't have a fixed meaning stored in a dictionary that you look up. Its meaning emerges from the company it keeps, from the words that appear beside it, near it, in the same contexts as it. You learn what a word means by watching it in use, many times, across many different situations. Word 2 vec, glove, BERT, GPT. Every major language model you'll meet in this course is, at its core, a mathematical implementation of this one intuition. We'll see it made explicit when we build word embeddings in session 2. Meaning doesn't live in the word. It lives in the relationships between words. If you take one thing away from this slide, let it be that. The third hard problem is about scale. And when I say scale, I mean numbers that should genuinely make you pause. Start with the vocabulary. English has about 170,000 words in current use. A practical NLP vocabulary, the set of tokens a model actually works with, typically runs to somewhere between 50 and 100,000 items. That already sounds large. It's nothing compared to what comes next. Ask yourself, how many different 10-word sentences are possible if the vocabulary has 100,000 words? 100,000 to the power of 10. That's 10 to the 50. Now anchor that. The biggest training corpora in existence hold maybe 10 to the 13 sentences. 10 to the 50 versus 10 to the 13. The gap is astronomical, and 10 words is a short sentence. Here's the implication. A language model cannot work by memorizing the sentences it might encounter. That's mathematically impossible. It has to learn the underlying patterns of language, the structural rules, the statistical tendencies, the semantic constraints, so it can handle sentences it has never seen. Generalization isn't a nice-to-have, it's the whole problem. And it gets worse. Scale has a cruel structure to it, and I want you to see it with your own eyes. Here's the question. How often does each word actually occur? Take a real corpus, count every word, and rank them from most common to least. Before the chart appears, take a guess at what that curve looks like. Here are our axes. Word rank along the bottom. The most common word is rank 1, The second most common is rec 2, and so on. Frequency on the vertical, measured relative to that top-ranked word. And notice both axes are logarithmic. Each step is a factor of 10. Keep that in mind for what you're about to see. Look at that. A straight line. On log axes, a straight line means a power law. Frequency is inversely proportional to rank. The top-ranked words, the, of, and, are enormously more common than everything else. And from there, it just falls and falls and falls. The blue dashed line is the idealized law, frequency proportional to 1 over rank. And look how closely the real data hugs it. Now look at the red annotation. Half the vocabulary of English appears fewer than 5 times per million words of text. Half. You might be thinking, surely more data fixes this. Fair, but it doesn't. Grow the corpus and new rare words keep arriving, so the tail never empties. This is data sparsity, and you can't learn from what you don't see. The name for this regularity, and you'll meet it again in the lab, is Zipf's law, after George Kingsley Zipf, the Harvard linguist who documented it across languages in the 1930s and 40s. It holds, remarkably, in every natural language ever checked. The fourth and deepest hard problem. Let me give you 2 sentences. Here's the first. The city council refused the protesters a permit because they feared violence. Who feared violence? The council. You almost certainly got that immediately. But notice what you just did. Nothing in the grammar picks out the referent. The pronoun they could point at either the council or the protesters. Both are third-person plural. Both are in scope. To choose, you drew on implicit knowledge about how civic authorities work and what kinds of institutions worry about public disorder. Now, try this version. Watch what happens. The protesters demanded a permit from the council because they feared violence. Now, who feared violence? The protesters. Why? Because that scenario, a group of people seeking official permission, partly out of fear of what might happen without it, fits what we know about how the world works. Councils issuing demands out of fear is a much less typical configuration. To resolve these pronouns, you need a model of the world. Not just a dictionary, not just a grammar. You need to know about power, causality, and typical behavior. None of that's written down in any grammar book. A machine that learns only surface statistics will struggle here. A machine that has absorbed an enormous amount of human text, and through it a model of how the world works, has a fighting chance. Hold that thought. It's one of the deepest arguments for large-scale pre-training, and we'll come back to it in session 10. You now own the 4 problems. So before we get to solutions, let me give you a compressed tour of how the field has fought them for 75 years. The whole history compresses into 4 eras, and here's the pattern I want you to watch for. Each era was a genuine breakthrough. Each era hit a ceiling it couldn't break, and that ceiling is exactly what motivated the next revolution. Era 1, the rule-based era, from the 50s through the 80s. You write the rules of language down, explicitly, by hand. Era 2, the statistical era. Stop writing rules. Count. Era 3, the neural era. Words become vectors, and you'll watch meaning become geometry. And Era 4, the one we're living in, the transformer era. In other words, each era's ceiling became the next era's starting gun. We'll spend the next 4 slides walking through these one at a time, and I want you to watch how the villain, the unsolved problem, changes shape at every step. The first era, rule-based systems. This is where it all begins. The logic was elegant. Language has rules, grammar, syntax, logical structure. So here's the engineering response. Write those rules down, build a parser, and apply them systematically. The theoretical foundation came from Noam Chomsky in his 1957 book, Syntactic Structures. A finite set of rewrite rules, he showed, can generate an infinite number of grammatical sentences. That's a profound insight. And for roughly 3 decades, researchers built increasingly sophisticated rule systems on top of it. Formal grammars for English took years of expert linguist time to construct. And in 1966, Joseph Weizenbaum built a program called ELIZA at MIT. 200 pattern matching rules, playing the role of a psychotherapist, reflecting your own words back at you. Remarkably, people found it emotionally engaging. Some users genuinely believed they were talking to a real therapist. Weizenbaum was disturbed by this. He built a mirror, and it fooled people. But here's the problem. Eliza understood nothing. And the deeper issue with all rule-based systems is that language has exceptions, an enormous number of them. Every rule needs subrules. Subrules need sub-subrules. The systems became impossibly complex, brittle to any novel input, and unable to scale. When someone typed something the rules had never seen, the system simply failed. And in the early 1990s, it did. Watch the shift. It's a philosophical one. Instead of writing rules, count. Give a machine enough text, and the regularities of language emerge statistically. You don't need to tell it that the is usually followed by a noun. The frequency tables show it. This felt almost like giving up on understanding, but it worked. The canonical statistical model is the n-gram language model. Look at the formula. Instead of asking what a sentence means, you ask, given the previous few words, what word is most likely to come next? That's a probability you can estimate by counting a corpus. How often does word C follow words A and B? Simple, scalable, and good enough to build real systems. IBM used statistical models to build the first workable machine translation systems. Hidden Markov models powered speech recognition that shipped in products you could actually buy. This era produced things that worked, in a way rule-based systems never quite had. But counting has a ceiling, and you've already seen it. In a count-based model, cat and feline are complete strangers. They rarely appear in the same immediate contexts, so a frequency table has nothing to say about their relationship. And remember the 10 to the 50 from 3 slides ago? Most sentences a deployed model meets were never in its training counts at all. Then, in 2013, something happened that I think genuinely deserves the word breakthrough. A researcher at Google named Tomas Mikolov published Word2Vec. Here's the idea. Stop representing words as sparse counts. Represent each word as a dense, learned vector, typically around 300 dimensions, trained on enormous amounts of text so that words appearing in similar contexts end up close together in that space. And when you do this, something astonishing happens. Meaning becomes geometry. You can do arithmetic with word meanings. King minus man plus woman. That vector lands next to queen. The direction of royalty is encoded in the geometry of the space. This is Firth's company it keeps, the quote from 6 slides ago, turned into mathematics. The first time I saw this, I stopped and stared at it for about 2 minutes. At the same time, long short-term memory networks, LSTMs, were revived for sequence modeling, letting models carry information across much longer stretches of text. And in 2014 to 2015, Dmitry Bahadinal, with Kyunghyun Cho and Yoshua Bengio, introduced the attention mechanism as a 2014 preprint published at ICLR in 2015, letting a model learn what to focus on. You'll meet both properly in sessions 3 and 4. Those were the ingredients for what came next. But LSTMs had a fundamental flaw. They process tokens one at a time, left to right. So training can't be parallelized efficiently, and information from the start of a long sequence gets diluted by the end. Attention helped, but it was bolted onto a sequential machine. Hold that thought. The next breakthrough would need something more radical. And in 2017, it arrived. A paper from Google, Attention is All You Need, by Ashish Vaswani and 7 colleagues, published at NeurIPS in 2017. A new architecture that threw the recurrence away entirely. No LSTMs, no convolutions, just attention, applied in a carefully structured way. They called it the transformer. Training became massively parallelizable, long-range dependencies were handled naturally, and the field changed almost overnight. Look at this table with me. BERT large in 2018, 340 million parameters. GPT-3 in 2020, 175 billion. GPT-4 in 2023, estimated at around 1.8 trillion, though OpenAI has never confirmed the number. And DeepSeek V3 in 2024, 671 billion parameters total, but only 37 billion active per token, showing what mixture of experts can do. We'll unpack every row of this table in sessions 8 and 9. We went from interesting research tool to passes the bar exam in 5 years. If that doesn't make you sit up, I'm not sure what will. And we need to understand why it happened, not just that it did. So let me be concrete about where things stand right now. What can these systems actually do? Start with exams. They pass professional licensing exams: law, medicine, finance, software engineering. Often not just barely, but in the top percentile of human test takers. They write and debug production quality code across dozens of programming languages. This is genuinely changing how you and I build software. They translate between more than 100 languages with near human fluency. For many pairs, the quality now rivals what you'd get from a professional translator. They summarize, they reason through multi-step arguments, and they've gone multimodal. Give them a description, and you get back an image, an audio clip, a short video. And they use tools. They browse the web, run code, call APIs, and in deployed systems, operate computers directly. You can ask a model to book you a flight. And yet, here's our villain, making its return. They hallucinate facts with total confidence, citing papers that don't exist. They fail counting tasks a 10-year-old would ace. They can be manipulated by crafted prompts. And they don't reliably know what they don't know. None of this is a reason to dismiss these systems. It's a reason to understand them deeply, which is exactly what this course is for. So where do we go from here? Let me show you the road. 14 sessions. 14 stops on one road. Read a few of the names. Words as vectors, attention, the transformer, scaling laws, training and alignment, hallucination. Every one of them is a solution to a problem created by the stop before it. And this is you, session 1, the very first dot. Everything you felt today, the ambiguity, the scale, the missing world knowledge, is the fuel for everything that follows. The road has 3 phases. Foundations, sessions 1 to 5. Vectors, sequences, attention, the transformer itself. Architecture, sessions 6 to 9. BERT, GPT, scaling laws, and the model zoo. And the real world, sessions 10 to 14. Training, efficiency, retrieval and agents, trust, and ethics. By session 14, I want you to look back at this line and understand in genuine depth what every single dot represents. Let me be specific about what I expect from you. Not vague learning outcomes, concrete things you'll be able to do. You'll be able to explain how the transformer architecture works mathematically. Not just wave your hands at attention. Actual matrix multiplications, actual softmax, actual positional encodings. You'll implement self-attention from scratch in PyTorch. Every line. When you're done, you'll know exactly what happens inside the model, operation by operation. You'll fine-tune a pre-trained model for a task of your choosing, and you'll understand what fine-tuning actually does to the weights, why it works, and when it fails. You'll build a full retrieval-augmented generation pipeline, a system that answers questions from documents it was never trained on. That's the architecture behind most serious production assistants right now. You'll build an agent, a system where the model reasons about which tools to call, calls them, and folds the results back into its answer. Agents are where the most interesting applied work is happening in 2026. You'll be able to critically evaluate what these models produce. Not just right or wrong, but why, and what the literature says about fixing the failures. And you'll be able to reason seriously about the ethics and societal impact of these systems, not as an afterthought. You're going to understand the machine from the inside out. That's my promise to you. Every good story needs an unresolved problem to carry you to the next episode. We end where the next session begins, with the question of how a machine should represent a word at all. Look at the left panel. This is one-hot encoding, the naive way to turn words into vectors. Each word gets a vector as long as the whole vocabulary, all zeros except a single one. You might be wondering, why not just hand the machine a synonym dictionary? Because someone would have to write it for every word, in every language, forever. Labels don't scale. And look at the deeper problem, the fatal one. Cat and feline are orthogonal. Their similarity is exactly 0. So is every other pair. Every word sits the same distance from every other word. The representation is mathematically useless for meaning. Now look at the right panel. Dense word embeddings. Learn from data. Cat, kitten, feline. Clustered. dog and puppy, clustered nearby. The motion verbs, off in their own region. Similar words are geometrically close. The geometry encodes the meaning. This is where we want to get to. And there's the question in gold, the one this session leaves you with. How do you get from the left panel to the right one? In plain words, how do you learn that geometry from raw text alone? With no labels, no annotations, no supervision. You just have words, billions of words, and somehow meaning has to emerge. That's the problem Session 2 solves. We'll build Word2Vec from the ground up, understand exactly why it works, and see for ourselves that the geometry of meaning is real. Before you go, a quick word about what you'll do in the lab. It's a 2-hour session on Google Colab. Nothing to install. Open the notebook, run the first cell, and everything is set up for you. You'll start by loading a real text corpus. You'll count words, look at distributions, and get a feel for what text looks like as data. Not a description of data, actual data in your hands. You'll discover Zipf's law yourself by plotting your own frequency counts. I could just show you my chart again, but I want you to watch that straight line emerge on a log-log scale from data you processed. That, oh, it really is a power law moment is worth 30 minutes of my lecturing. You'll build a bag of words model, the simplest possible text representation, and use it to hunt for similar sentences. And you'll watch it fail. Beautifully, instructively. The failure makes it absolutely clear why we need something better. You'll find sentences in the corpus where the same word carries completely different meanings. And you'll see in your own data why a model that ignores context can't tell them apart. And finally, my favorite part, you'll build a simple keyword question answering system and then spend 15 minutes deliberately breaking it, every way you can think of. Document how it fails and why. The goal of today's lab isn't to solve anything, it's to feel the problems. In other words, to have a hands-on encounter with what makes language hard, so that every technique I introduce in sessions 2 through 14 has a concrete reason to exist in your head. Open the notebook, run the first cell, and off you go. I'll see you in the lab.